Welcome to the deep dive.
Glad to be here.
So we have this absolutely fascinating stack of field notes today. Architectural diagrams, raw debug captures.
Yeah, a real treasure trove.
It really is. It was provided to us by a developer named Terry, and it's all detailing this reverse engineering tool called Regmon, which I guess is part of a broader diagnostic suite called the FossilCrew stack.
Right, exactly.
And what we're doing today is looking at a highly specific, real-world debug capture of a microcontroller. Our mission for this deep dive is to deconstruct exactly how this tool, extracts operational secrets from silent silicon.
Which is a lot harder than it sounds.
Oh, totally. I mean, imagine you're sitting at a workbench, right? You have a target board in front of you with a microcontroller on it.
Just a black box, essentially.
Exactly. Someone just hands you this board and says, figure out exactly what the firmware is doing at this very second.
No pressure.
Right. And the constraints here are severe. I mean, they represent the reality of advanced hardware analysis in the field. You do not have the source code.
No source code at all.
None. You don't have a pre-analyzed binary to just drop into a disassembler. And the ultimate restriction, the one that really turns this into a locked room mystery, is that you cannot pause the live chip.
That's the kicker.
You can't halt the CPU, you can't set a breakpoint, you can't interrupt its execution flow in any way, because doing that might, destroy the volatile state or the timing behavior you're actually trying to observe.
Yeah, you have to monitor this thing while it's actively running.
Which feels like a magic trick.
It really does. But those constraints, they perfectly frame the fundamental challenge of black box dynamic analysis.
Right.
When you attach a normal debugger and issue a hold command, you are inherently altering the environment.
Because you're stopping the world.
Exactly. You might miss a race condition, or, you might cause a watchdog timer to bite and reset the entire system.
Oh, wow.
Yeah. Or you could just disrupt this really delicate communication protocol happening on the bus. So the ability to deduce the internal state of a microcontroller without stopping its execution, well, that's what separates basic troubleshooting from professional reverse engineering.
Which is exactly what this deep dive is tailored for, right? Beginner electronics students and field technicians looking to level up.
Absolutely. The Regmon captures we're looking at today demonstrate this amazing methodology for extracting the true internal pulse of the machine.
By using the hardware against itself.
Exactly. Leveraging the hardware's own diagnostic architecture to just move completely beyond the surface-level assumptions that, frankly, mislead a lot of field technicians.
Okay, let's unpack this. We need to start with the very first step of this analysis, which involves unmasking the silicon.
Right, step one.
And what stands out immediately in Terry's documentation of Regmon is, well, the tool's absolute insistence on certainty before it does anything else.
It does not guess.
Right. It doesn't rely on user input to know what target it's attached to, and it doesn't try to guess based on, heuristic probing that might accidentally crash the board.
Which happens all the time with cheaper tools.
Yeah. It just leverages the debug interface to demand a hard-coded identity directly from the silicon itself.
In a traditional bench setup, a technician might spend a totally frustrating amount of time just trying to verify the exact variant of the hardware they're interacting with.
Squinting at the tiny text on the chip.
Oh, yeah. Cross-referencing part numbers etched on the package. And those can sometimes be counterfeit or obscured or just completely misleading.
So Regmon just bypasses the physical package entirely.
Entirely. It uses the serial wire debug protocol SWD to reach right into the chip's debug access port.
Okay, so talking directly to the brain.
Well, more like the nervous system. Through the ARM core site architecture, the tool can perform these background memory accesses on the system bus without ever actually interacting with the CPU core itself.
Wait, really? It doesn't even talk to the CPU?
Nope. It navigates to a specific standardized memory address, usually the DBGMCUID code register in STM32 devices. Yeah. And it reads the burned-in silicon identity code.
So it basically asks the hardware directly at the bus level, what are you?
Yes. And it retrieves a definitive, unforgeable hexadecimal answer.
Okay, and the capture provided in our sources shows exactly what the tool retrieved here. The output reads, let me find it here, chip. STM32F1 F103 class. DVID 0x410.
Here you go.
So the tool has positively identified the silicon as belonging to the STM32F1 family, specifically the F103 performance line.
Right.
But that DVID of 0x410, that's the immutable proof.
It is. That is the manufacturer's internal tracking IV for that specific silicon die revision and its exact feature set.
Okay, I see.
What's fascinating here is how the tool leverages that unshakable certainty to basically automate the rest of the environmental setup.
Oh, so it sets up the workspace automatically.
Precisely. Because it retrieved DVID 0x410, Regmon instantly knows the entire memory topography of the target.
It just knows it.
Yep. It automatically pulls up a file called stm32f103.db, which acts as this architectural blueprint for the rest of the analysis.
Okay, so what is that .db file?
That file is based on the SVD standard, the system view description.
Okay.
CMSIS SVD is this XML-based schema defined by ARM, and it meticulously maps every single peripheral, register, and bit field within a specific microcontroller family.
So this is like, okay, imagine you're walking into a completely dark, unknown building. But the second you step through the door, someone instantly hands you the exact architect's blueprint for the entire floor plan.
That's a great way to put it.
It instantly gives you the terrain map you need, because otherwise, a technician would have to manually cross-reference, what, a 2,000-page PDF manual?
At least. Just to figure out which random hexadecimal memory address corresponds to which control register.
That sounds like a nightmare.
It is. But the SVD file provides a machine-readable dictionary. The tool parses this huge XML tree, and it links those raw hexadecimal memory addresses to human-readable names and structural definitions.
So it does the heavy lifting for you.
Exactly. The SVD database defines the exact boundaries of the memory-mapped I/O. So it tells the tool that, hey, if you read a 32-bit value at address 0x40001000, you are looking at the reset and clock control block.
Got it.
And even better, it defines what bit 4 of that specific register means, whether it's read-only or read-write, and what its reset value should be.
Wow. Okay.
So by automating the ingestion of that SVD file based on the DVID, Regmon completely eliminates the cognitive load of manual address translation.
So the reverse engineer can just instantly start querying peripheral states by name.
Yes, knowing the tool is securely translating those queries into precise, non-intrusive background memory reads via the debug probe.
Okay, so now that we have the terrain mapped, Regmon immediately performs its first active check of the system's state. It queries the RCC, right? The reset and clock control block.
That's the one.
And from what I understand, in the context of modern ARM microcontrollers, the RCC is essentially the master power distribution network, like the master switchboard.
That's a perfect analogy.
Because microcontrollers don't just supply power to everything at once, right? They use these complex clock trees and clock gating to aggressively manage power consumption.
Exactly. Power management in modern silicon is a massive, massive design priority, primarily to minimize dynamic power dissipation.
Right, because every time a gate switches, it uses power.
Every single time a digital logic gate toggles, it consumes power. So if a peripheral, let's say a serial port or an analog to digital converter, if it's not actively being used by the application, supplying it with a continuous clock signal is just a huge waste of energy.
So they just turn the clock off for that specific part.
Yep. Therefore, the RCC block contains a series of enable registers. You'll see names like HBBNR, APB1ENR, and APB2ENR.
Okay.
And these act as discrete switches. By default, out of reset, almost all of these switches are completely turned off.
Oh, so the chip wakes up mostly dormant.
Exactly. The firmware has to explicitly write to the RCC registers to enable the clock signal to a specific peripheral before it can even configure it, let alone use it.
And if it doesn't?
If you try to read or write to a peripheral that has its clock disabled, the bus transaction will typically just stall, or it'll generate a hardware fault.
Got it. So looking back at the capture from Terry's notes, it shows Regmon reading these specific clock enable registers to see what the firmware has actually turned on.
And what did it find?
Well, the results are incredibly sparse. The tool reports that only FLIF and SRAM are clocked. That's it.
Just those two?
Yeah. So FLIFRA is the flash memory interface, which manages read access and wait states for the internal flash memory where the code actually lives. And SRAM is the controller for the internal static RAM used for the stack and the heap.
Right. And those two controllers, they are the absolute bare minimum requirements for the Cortex-M core to execute any code whatsoever.
Like just to survive.
Pretty much.
Right.
It needs the flash interface to fetch instructions, and it needs the SRAM controller to push and pop data from the stack. The fact that only these two are enabled tells us something highly specific about the state of the extremities of this chip.
Because what is disabled is a massive list. I'm looking at the capture, and it shows no GPIO ports are clocked, no timers, no UARTs, no SPI, no I2C, no USB, no ADC, and no DMA controllers.
It's totally locked down.
Yeah. Every single peripheral designed to allow this microcontroller to communicate with the outside world or read a sensor or move data.
Yeah.
It's all sitting completely dormant, just totally gated off from the system clock.
Which is very telling.
But wait, let me push back on this for a second. If a field technician or a beginner student is looking at a board and their diagnostic tool shows that every single external interface and internal peripheral is clock gated off, wouldn't the most logical conclusion be that the chip is just dead? Or idle, like doing absolutely nothing?
And that right there is the naive trap.
The naive trap.
Yes, that is exactly the trap that catches so many people who rely on basic diagnostic methodologies.
Oh, really?
Oh, definitely. Many standard tools, like standard logic analyzers or basic JTAG debuggers, they might dump the peripheral state, see the RCC registers sitting at their reset values, and just instantly conclude the target is inactive.
I mean, the logic seems sound on the surface, right? If the system has no way to read inputs or generate outputs, it can't be doing any meaningful work.
Right. The technician might assume the board is bricked or stuck in a reset loop,
Yeah.
and then they would start completely going down the wrong rabbit hole, troubleshooting the power supply or the reset line.
Right. It's like seeing a quiet factory floor with no trucks leaving the bin and just assuming the whole company is out of business.
That's exactly it. But relying solely on the RCC state is a fatal flaw in dynamic reverse engineering.
Why is that a fatal flaw?
Because stopping at the clocks completely ignores the true pulse of the system. The state of the peripheral clock tree dictates absolutely nothing about the state of the CPU core itself.
Wait, really? They're totally disconnected like that.
Yeah, the Cortex-M core operates in its own independent clock domain. Typically, it's driven directly by the core system clock, or HCLK.
Okay.
So a microcontroller can have every single peripheral disabled at the RCC level, yet the CPU core could be running at maximum frequency.
Doing what if everything is off?
It could be executing a complex cryptographic hash in SRAM. It could be crunching through a mathematically intensive floating point algorithm. Or, as we're going to see, it could be trapped in a logical error state.
Wow.
The clock settings only describe the routing of the signals to the peripheral buses. They provide absolutely zero visibility into the instruction pipeline of the processor core itself.
Here's where it gets really interesting. Regmon is designed specifically to avoid this naive trap.
It is.
It doesn't stop its analysis at the RCC block.
Right.
Instead, it leverages that core-side architecture we mentioned to ask a secondary, completely vital question.
The most important question.
Right. Not what the peripherals are doing, but what the CPU core itself is doing. Is it actually fetching and executing instructions? And it does this by sampling the program counter.
The program counter, or R15 in the ARM architecture, that register holds the memory address of the current instruction being executed, or more accurately, in a pipelined architecture, the instruction being fetched.
Okay, so it's pointing to the current task.
Right, so monitoring the program counter over time provides the definitive footprint of the CPU's execution flow.
But wait, how do you read that without pausing the chip? I thought standard debuggers require you to halt the core to read core registers like R15.
They usually do. However, Regmon utilizes a technique of non-intrusive sampling.
Okay, how does that work?
Through the debug access port, it can repeatedly query the debug hall control and status registers, or it can utilize the data watch point and trace unit. This allows it to sample the PC value while the core is running at full speed.
Okay, that is super clever. So it's just taking snapshots of the address while the engine is running.
Exactly. Over a couple of seconds, it grabs these snapshots.
Well, the capture data from Terry's stack gives us the raw PC samples that Regmon pulled over its observation window. Let me read out the exact captured values for you to visualize.
Over it.
The tool reads the program counter 6 times, and it returns these exact hex values. 8954, 8954, 8954, 8958, 8958, 8954, 8954.
Let's analyze the math of that execution footprint, the delta there.
Yeah, because it's definitely not incrementing sequentially through memory, which would indicate like normal linear code execution, right?
Nor is it returning a single static value, which is what you see if the core were halted or in a WFI, a wait for interrupt sleep state.
It's bouncing back and forth.
Yes, the values are oscillating perfectly between 8954 and 8958.
And the mathematical difference between those two numbers, 8958 minus 8954, is exactly 4 bytes.
And that 4-byte delta is highly revealing when you apply the context of the ARM Cortex-M architecture.
Okay, break that down for me.
So the STM32F103 executes the ARM thumb dash instruction set.
Thumb 2, got it.
Unlike classic 32-bit ARM instructions, thumb instructions are designed for extreme code density. In the standard thumb set, Nearly all instructions are exactly 16 bits wide.
Which is 2 bytes.
Exactly. Now, Thumb 2 introduced some 32-bit instructions mixed into the same stream, but a vast majority of basic logical and branching operations remain 16-bit.
So if we have a gap of exactly 4 bytes in memory, that equates to exactly 2 16-bit instructions.
Yes, if we connect this to the bigger picture, this oscillating program counterproves, beyond a shadow of a doubt, that the CPU core is not idle.
Not even a little bit.
It is actively executing a tightly bound, continuous loop. The execution pipeline is fetching an instruction at 8954, executing it, fetching the next instruction, and then immediately branching straight back to 8954.
So it's just spinning in a circle.
The core is running flat out, toggling back and forth across a 2-instruction loop body. It completely contradicts the quiet state implied by the disabled peripheral clocks we saw in Phase 2.
Okay, so Regmon's output at this stage is actually brilliant because it doesn't just present the raw addresses and leave the reverse engineer to guess what they mean.
No, it actually lays out candidate explanations, honestly.
Right. Rather than projecting false certainty, it embraces the ambiguity of black box analysis. It gives us the 2 most statistically probable scenarios for this exact footprint. And candidate 1 is the classic busy wait spinlock.
A busy wait spinlock is a really fundamental synchronization primitive in embedded systems.
Okay, when would a developer use that?
It's used when the firmware needs to wait for a specific condition to become true, usually a hardware flag changing state, and the latency requirements are so strict that the overhead of an interrupt or an RTOS context switch is just unacceptable.
Ah, so it just stares at the flag waiting for it to flip.
Exactly. At the C code level, this is typically written as a while loop, evaluating a volatile variable or a memory-mapped register bit, like while not flag.
And when that C code is compiled down to ARM assembly, you're saying it fits the 4-byte footprint perfectly.
Perfectly. The compiler will generate 2 16-bit instructions.
Which are what?
The first is a load and compare. It reads the target memory address into a register and compares it against a 0 or a non-zero value. The second instruction is a conditional branch. If the condition isn't met, branch straight back to the load instruction.
Load and compare, then branch back, 2 bytes plus 2 bytes, 4 bytes total.
Right. And the mechanics of this spinlock completely explain the oscillation between 8954 and 8958. The CPU executes the load, fails the condition, executes the branch, and loops back forever.
But wait, when we contextualize this spinlock hypothesis with what we discovered earlier regarding the RCC block, the implications are, like, horrifying for the firmware.
Why is that?
Well, because if this loop is waiting for a hardware peripheral flag to change, say waiting for a UART transmission to complete or an ADC conversion to finish, that flag will never ever change.
Oh, because of the clocks.
Yes. The RCC check proved that the UART and the ADC do not have a clock signal. The peripheral hardware is completely unpowered and incapable of updating its own status registers.
So, if candidate 1 is true, this chip is entirely hung. It's stuck in an infinite loop, waiting for something that can physically never happen.
It is deadlocked.
Exactly.
And that's actually a classic firmware bug. It's often caused by an improper initialization sequence. You know, a developer might write code that attempts to transmit a string before explicitly enabling the UART clock in the APB2 ENR register.
So the CPU enters the transmission function, hits the spin lock, waiting for the transmit buffer to be empty.
And hangs forever,
For
screaming along at 72 megahertz, burning power, checking a flag on a peripheral that cannot respond.
Wow. So the tool has essentially diagnosed a catastrophic hang state without ever seeing a single line of source code.
It has.
But the FossilCrew stack documentation also outlines candidate 2, which provides a completely different functional interpretation of the exact same PC footprint.
And what's that?
Candidate 2 suggests the target is running a 4th kernel, specifically the micrisp Stellaris implementation. Micrisp Stellaris. 4th is a highly optimized stack-based programming language. It's heavily utilized in certain embedded environments for its extreme interactive capabilities and incredibly low memory footprint.
Okay, but how does it run differently than C?
Well, a 4th system doesn't operate like a standard compiled C program. It operates via an inner interpreter.
An inner interpreter. Okay.
Right. Micrisp Stellaris compiles words into memory and uses a specific threading model to execute them. The core of this system, the engine that actually drives the execution from one 4th word to the next, is this tiny routine, often referred to as NAXT.
Okay, so how does that explain our 4 bytes?
In a direct threaded or subroutine threaded 4th implementation on an ARM architecture, when the system is sitting at the interactive prompt, just waiting for the user to type a command over the debug link or a serial port, It drops into a master polling loop.
It's just waiting for input.
Yes, the mechanics of that inner polling loop involve checking an input buffer. And if no data is present, it branches back to the start of the check.
Just like the spinlock.
It's exactly like it. In this specific optimized assembly of micrisp stellaris, the idle polling loop, the state where the kernel is perfectly healthy, stable, and just waiting for the next character, it compiles down to an incredibly tight sequence of instructions.
And it results in the exact same execution profile we're observing.
The program counter bounces rapidly between the instruction that checks the input state and the branch instruction that loops it back.
So we essentially have two drastically different realities here.
Very different.
Candidate 1 means the firmware is fatally bugged, it's trapped in a hardware deadlock. But candidate 2 means the firmware is a sophisticated, interactive interpreter idling perfectly, just waiting for a user command.
Yep.
It's honestly it's like comparing a car whose transmission has snapped and the engine is redlining while stuck in neutral versus a highly tuned sports car sitting at a red light with the engine idling flawlessly.
That's a really good analogy.
To an observer just listening to the raw engine sound, or in our case, just watching the program counter bounce across 4 bytes, the mechanical footprint sounds absolutely identical.
And that distinction perfectly highlights the limitation of purely dynamic observation. The side effect, the oscillating PC, is identical. Dynamic analysis can pinpoint the exact location and shape of the behavior, but it can't always infer the intent behind the code.
But the tool still lays it out for you.
Right. The tool correctly identifies that a 2-instruction loop is executing, and it wisely provides both the error state hypothesis and the environmental hypothesis based on the context.
Wait, hold on. Let me throw a wrench in this. If we are seeing the program counter bounce between 2 specific addresses, couldn't that just be an interrupt storm?
An interrupt storm.
Yeah. Like if a hardware alarm or an external pin is constantly triggering an interrupt request, wouldn't the CPU be jumping back and forth constantly? And couldn't that look exactly like this oscillation?
This raises an important question about how to read the actual footprint of CPU behavior and how we can systematically rule out the interrupt storm theory using the mechanics of the ARMM exception model.
Okay, so Regmon's methodology dismisses the interrupt theory.
It implicitly dismisses it based on the purity of the sampled register data. Let's break down the anatomy of an interrupt on the Cortex-M.
Okay, let's do it.
When an interrupt fires, the NVIC, the nested vectored interrupt controller, takes over. The CPU doesn't just instantly execute the handler.
Right, there's process.
A highly complex entry sequence. When an interrupt request is accepted by the NVIC, the CPU first has to suspend its current context.
It has to save its place.
Exactly. It pushes 8 critical registers R0 through R3, R12, the link register, the program counter, and the program status register. It pushes all of those onto the active stack.
Oh, wow, that's a lot of overhead.
It takes several clock cycles. Once the state is finally saved, the CPU fetches the exception vector from the vector table, loads that specific address into the program counter, and only then begins executing the interrupt service routine, or ISR.
And when the ISR completes,
it executes an exception return. That triggers the unstacking process, pulling those 8 registers back off the stack and restoring the original program counter so it can resume the main thread.
Okay, so because of this massive sequence of event stacking, fetching the vector, executing the prologue of the handler, the body, the epilogue, and unstacking, an interrupt storm would create a totally massive scattered footprint in the program counter.
Exactly. If a hardware timer or an external pin were generating tens of thousands of interrupts per second, the PC would be wildly distributed across memory.
It wouldn't just be 2 addresses.
Right. If Regmon took 6 random samples of the PC during an interrupt storm, it is statistically impossible that it would capture exactly 2 alternating addresses 4 bytes apart.
You'd catch it mid-save or mid-return.
You'd catch the PC in the middle of the main loop, then somewhere deep inside the interrupt handler at, like 0 by 0, 0, 0, 0, A, 0, A, 0. And then maybe during the exception return sequence, you'd see this wide scatter plot of addresses.
But the fact that the tool captured exactly 8954 and 89588 6 times in a row with 0 outliers, that definitively proves the loop is deterministic and unbroken.
Yes, the CPU is trapped in a completely predictable 2-step dance. An interrupt would introduce chaotic jumps to distant memory region.
Okay, I see.
So the raw mathematical consistency of the sampled data completely rules out an interrupt storm. It guarantees we are dealing with a tight, infinite software loop.
So what does this all mean? Like, how does a reverse engineer or a field technician actually use this specific data in their workflow?
Well, let's look at what we know. We've used Regmon to prove the chip is actively executing code despite the clock suggesting it's dead.
Right.
We have mathematically ruled out an interrupt storm.
Yeah.
And we know it's a two-instruction loop residing exactly at 0 by 8954.
But how do we solve the mystery of whether it's a broken spinlock or a healthy fourth interpreter?
This is where we see the absolute synergy between dynamic register monitoring and static binary analysis.
Yeah, okay, the handoff.
Exactly. Regmon has completed its role as a black box dynamic tool. It observed the live system, bypassed the deceptive peripheral states, and pinpointed the exact memory addresses where the critical action is happening.
But dynamic analysis can't translate those compiled machine instructions back into readable logic.
Nope. For that, the reverse engineer must transition to static analysis.
And the handoff is incredibly precise.
Yeah.
The technician doesn't need to dump the entire flash memory and spend 3 weeks reading tens of thousands of lines of assembly code just trying to find the main execution loop.
No, because Regmon gave them the exact zip code of the activity.
Right. So they take those two addresses, 8954 and 8958, and they feed them into a static disassembler like Ghidra or IDA Pro.
Or Redair 2, along with a dump of the firmware binary. The static disassembler acts as the translation layer. It converts those raw hex opcodes located at those specific addresses back into ARM thumb assembly language mnemonics.
Because Regmon provided the exact pointer, the technician simply navigates the disassembler directly to 0 by 8954. They don't have to trace the reset vector. They don't have to untangle the initialization branches.
They just look at the code residing at that specific address, and instantly, the static view will reveal the truth.
What will it show?
Well, if the disassembler shows an LDR instruction reading from a peripheral status register address, followed by a CMP and a BNE branching back,
Yeah.
the technician instantly confirms candidate 1.
It's a fatal busy wait spin lock hanging on unclocked hardware.
Exactly. But if the disassembler shows the characteristic register manipulation of the Mecris Stellaris NAXT return, handling the fourth instruction pointer, they confirm candidate 2.
It's a healthy interpreter polling for input.
Yep. The static disassembly provides the what, but the dynamic register monitoring provided the where.
The elegance of this methodology is just staggering when you consider the constraints we started with.
It really is magic.
By combining non-intrusive PC sampling with targeted static disassembly, the reverse engineer solved a highly complex behavioral mystery without ever halting the target.
No breakpoints.
Right, without triggering a single breakpoint and without having access to the original source code. The microcontroller continued to run flat out the entire time, completely unaware its internal secrets were being fully exposed.
It is the absolute pinnacle of non-destructive diagnostic methodology. You are deducing the internal state of a highly complex state machine solely by observing its side effects through a debug side channel.
Which saves so much time.
Oh, this workflow drastically reduces the time required to triage unknown firmware. It moves the technician from a state of complete blindness to precise, targeted code analysis in a matter of minutes.
So as we wrap up this deep dive into the FossilCrew stack and Regmon, I think the golden rule for field technicians, reverse engineers, and electronics students is abundantly clear.
Don't trust the clocks.
Don't trust the clocks. The outward-facing indicators of a system state are frequently deceptive, whether by design for aggressive power management or by accident due to firmware bugs.
A microcontroller can have every single peripheral disabled, appearing completely inert to standard logic analyzers and basic diagnostic checks, while the CPU core is simultaneously executing complex instructions at maximum speed.
Assuming that a quiet peripheral bus equals an idle processor is a fatal flaw in hardware analysis.
When you are troubleshooting silent microcontrollers, the clock settings are merely suggestions of intent. The program counter is the only true, unforgeable heartbeat of the machine.
And the actionable advice here is to always look past the RCC block. When a black box is sitting on your bench appearing quiet, leverage the debug architecture to peek at the program counter.
We will always tell you the truth.
Sampling the PC without halting the core will instantly cut through the assumptions and tell you whether that silicon brain is actively executing logic.
Master the synergy of dynamic and static analysis. Let tools like Regmon find the live execution loops, mathematically eliminate edge cases like interrupt storms, and use those precise addresses to laser focus your manual disassembly efforts.
Amazing. I want to leave you with a final, slightly provocative thought to mull over. We have just meticulously deconstructed how easily a trained technician can be fooled by the outward quietness of a microchip's peripheral clocks, masking a processor that is running at full throttle.
It happens all the time.
It really forces you to consider the broader implications. If we can be so easily fooled by a microchip, how many other digital systems or networks or connected devices in our daily environments do we implicitly assume are idle or off, simply because their outward-facing indicators are silent?
That's slightly terrifying thought.
Right. A screen is dark, an LED is off, a network tort seems down. But what hidden, continuous loops of complex activity might be running right now? Silently polling, waiting, or crunching data in the devices all around you. Just waiting for the right tool to observe their true internal pulse.